Okay, maybe we can get slowly started. So, good morning, everyone. So, yes, this morning, as you know, is a tutorial session that will be run by Natalia and myself. So, about basics of Lisa data analysis. So, mainly, we will introduce the waveform generators. I mean, common waveform generators that we use. Inference. So using samplers, in particular one that is commonly used today, which is called Erin. And we also show how to start analyzing, these Lisa data challenges where you have a blend of signals. So it's very introductory. So it starts slowly and easy. And so with massive black holes first, the first session will be devoted to massive black holes inference, and then Natalia will present to you, the analysis of galactic binaries, in particular the case where there are several. No, not several. Mm-hmm. Will you introduce machine learning as well? Yeah. So you will have a little bit about that as well. So regarding this first session of massive black hole binaries. It has 3 parts. So, it starts very basics, basically, with just, introducing this sampler, this Markov chain Monte Carlo sampler that we call Erin, and applying it to a toy example, which is nothing to do with gravitational waves. And then we'll start, generating our own data sets that contains a signal, and we'll try to do some simple inference on it. Just selecting a few of the parameters of the massive black holes, and then yes, there are first steps in downloading and visualizing and investigating Lisa data challenges data set, in particular the one that is called Sangria. So there are different names for the Lisa data challenges, and the more alcoholic rate there is in it, the most difficult it is to analyze. So yeah, up to now we've been analyzing Sangria, but the next one will be Mojito light, and then Mojito heavy, and so on and so forth. So the names have been chosen by Stas that you met. Okay, so. Getting started with this, I will do it with you so that I can do with your pace. Of course, for those who it's too simple, you can go ahead with the notebook. So there are some holes, some cells that you need to write down yourself. It's not a lot, but it's to also force you to participate into it. But I will give the solutions, of course, and maybe actually, and also I will upload the solution notebook. So we decided to go with Google Colab. It requires a Google account. So I'm sorry about that, but that's for avoiding the pain of installation problems. So what you need to do is click on the link that we uploaded in the school website. So you have to go to the Lisa school, and click on. Let's go to the timetable. And so you click on that analysis session, and there is this material link here, and so there are 2 links, one for the massive black hole tutorial and one for the galactic binaries. So we'll start with the massive black hole one. And that should direct you to this thing, okay? And so to use it, you need to do File and save a copy in Drive. So this is in French. So I will do actually the same as you. So, of course, if there are any issues with that, please tell me. So, the first thing to do So yeah, first I check if you are at this stage. Yeah, I see some heads nodding. Yeah. Okay. So first thing first, we need to install, the required packages. So there are not many of them, but the installation takes a while. You see, so we can start running this, right? So this first cell. Actually, it's common that it asks you to rerun it because for some package to be installed properly. So there are, a few packages here. So Lisa Data Challenge, it's a toolbox that has been developed to handle the data challenge data sets, the time series, to do some simple calculations. Also, it provides noise model, so power spectral densities of noise in Lisa, and a few other things. The second one is Lisa Beta. So this is a waveform generator for massive black hole binaries in the frequency domain, which is based on this phenomenological waveform model, PhenomG. So this, I think this version only has the 2-2 mode, but now it's it also features a PhenomHM, some with higher modes in it. Okay. And then you have chain consumer. So maybe some of you know this is a package that helps you to visualize outputs of samplers, to plot corner plots, inspect chains, and so on, in a nice way. It has some kind of features. And Erin. So Erin, this is this sampler that I was telling you about. So it features several things actually. So it's an ensemble sampler where you have different chains, different walkers working in parallel, and the proposals. I mean, you can choose proposals so that they are using the states of other walkers to propose new points. So usually they do that by randomly picking another walker and proposing a point that is in the middle or linearly. It's in the middle between your current state and the state of the other walker. So it's called ensemble sampler. So this is the basis. It's like EMCE, if some of you have heard about that. And it also features parallel tempering. So Stas told you about that, with the different temperatures that allow you to not get stuck into a local maxima, but really explore a different tempered version of the likelihood of the posterior, let's say. And the nice feature of it is that it's possible to do transdimensional inference. So using this reversible jump MCMC that also Stas presented to you. So it's kind of an all-in-one sampler, which is very nice. Okay, so as you see, it takes a while. I'm taking this opportunity to just have a look at what's next. So of course, there is all the importations that we will need. You have a recall of the Markov chain Monte Carlo method that Stas presented to you. So I will not go through this because you had this lecture. So it's a bit verbose, but it's a reminder, let's say. So it's still, the main algorithm of Erin is that, right? And of course, it has many things on top. Here you have a list of Markov chain Monte Carlo sampler if you want to try several of them. I'm not familiar with all of them, but so EMC is the one that Erin is based on. This ensemble sampler, we say it's an affine invariant sampler. There is Pi MC3, which I think uses probabilistic models. and I think also Hamiltonian Markov chain Monte Carlo. So it uses the gradient of the likelihood, and then you have many others that are listed here. And also, there are nested samplers. So the other type of sampler that Stas described to you, where you have these layers, that you explore iteratively. So first you start with the entire prior, and then you put a cap on the likelihood value. You start to exclude points that have likelihoods below a certain threshold, and you increase in likelihood values like that. Okay. So this is just, I'm going really quickly through the text. It's not, you can read afterwards. It's just reminders. So, and what we will do is really start really simple with, a toy model. So you have this, this data. Maybe I can write that. So you have, okay. So this is the time where you need to restart the session here, and rerun again the first cell. So I'm sorry about that. It works after that, but this is a requirement. So we go ahead and start the first cell again.
Some of it will install some libraries like NumPy.
Okay. So it's you reinstall things after installing the first things, like something like that. I don't know. Okay. So we'll start very simple, and actually, so we have some data that is actually will be described by some linear model. It's actually just a straight line, and a noise that is Gaussian and has a zero mean and variance sigma squared. Okay, so this is the data that we will use. So this is a vector n times 1. This is a matrix n times p, and this is a vector of parameters. Yeah, right. And this vector of parameters actually is just this m and this c here. Here you can see here, which is just the intersect of the y-axis and the slope of your line, okay, your straight line. So very, very simple. So let's see if it's finished here. Yes, okay. So we can start a little bit running things. So is everything okay so far? Like it works? Okay. So as you can see, this function straight line is just implementing the simple model. So you have, your data that is just this straight line plus some Gaussian noise, right? And so this Gaussian noise has, the likelihood is defined by the distribution of the noise. So here it will just be, or maybe the distribution of n will be equal to this, right? The usual. So actually it will be this and this. Actually there is a power of n here because you have many time samples. Okay, I don't know how many here in this simulation. So this is just I will make it like Stas wrote it. So this is your likelihood in a sense, right? Okay. And so we start, with, let's say, the frequentist approach. So instead of, rightly going into the Bayesian analysis, we start with a maximum likelihood estimator. So this function here, least squares, is just implementing the least square estimator. So when you have your log power spectrum, so your log likelihood, so it's if you consider that the noise is constant, that you don't fit for it, you will just have this term that will vary with the parameters, right? You will have something like this. And if you want to adopt the frequentist approach, then what you can do is finding the parameters that maximizes the likelihood, right? So you can do, you can do the derivative of the likelihood, of the log likelihood with respect to theta, right? So this is what you can do. And what you do when so theta is a vector, right? So, I mean, you can abuse of the notation of saying, okay, I'm maximizing with respect to a vector. And what you will find is something like that. It's like deriving, in a 1D function, but formally it's a bit the same, but at the end you have something like that. And you want this derivative to be 0. So you do that. And what you end up is something like that. Okay. And so the maximum likelihood estimator is given, for theta, right, is given by theta hat equals this thing inverse times transpose A times D. Right, so this is valid for any linear, model. Okay, and this is what I call the frequentist approach. Like you're doing a least square estimation. Okay, and this is what this function is implementing. Okay, so far so good. And if you look at the results of this estimation, you see this dashed green line, which is your maximum likelihood estimate. Actually, you could also compute what's the variance of this estimator, and we will use it afterwards. So I would say the variance of this estimator would be this, right? You take the brackets of the variance of D times A transpose A, minus 1. And this variance of the data is just sigma squared. So actually, you will have ATA which cancels, and you will end up with this. So in this frequentist approach, you will have, both an estimator that is given by this formula and its estimated variance, in case you have not done any mistake on your noise and you know exactly what the noise statistics are. Okay. So then, what do we do when we want to approach this problem, this simple problem, in a Bayesian way? Well, we keep this likelihood, of course. This is the distribution of the noise, and we also stipulate a prior distribution for the parameters. So the parameters here this is just MNC, right? And in this simple case, we will use a uniform prior, okay? So, okay, so this is the derivation of the log likelihood. And so the first exercise is just to write down this likelihood, the log likelihood rather, because this is the piece that we will need for the Bayesian estimation. Okay. The prior is already given. We take, uniform prior for M and uniform prior for C, and it's given by, well, this, normalized formula. But I guess you've done. You can do it if you want. What do I mean? Yes, I can. If you're awake enough, Yeah, but basically this is implemented this. So in that case, since you have already this straight line function available, you can use that to fill this likelihood function. Yes. I could write it myself. Yeah. See if I can. Yeah.
Should we change the argument list?
The argument. Yes. Okay. I think initially I was using global variables, but you're right. You can also take it as a proper arguments, as a good coder should do. How did I do that?
Between your approach and then having the list of 4 parameters.
Is it, sorry, what's the question?
So what's the difference between having this global
okay. So the problem with having global arguments is that if in case you want to change something and reuse your function, that would be much easier if it takes as arguments everything it needs to do the computation, right? Because otherwise, if it relies on something you have defined ahead of time, it can be confusing. Maybe you have a better argument.
No, it was just about the arguments. If you want to add the other arguments as in the log likelihood function, you have to put them as optional arguments with default values, because if you don't do that, then the sampler will complain. You have to have only theta as an input, as a mandatory input.
Yeah, this is a good point. So when you use a log likelihood, indeed, if the likelihood only has as input the parameter vector, it's fine. If it has additional parameters, you should put them as keyword arguments and tell the sampler So either leave it like that, or tell the sampler, okay, here are the keywords arguments, so the additional arguments for your likelihood function. Yeah, so I didn't think about that. For Erin, it's important. So let's see, how we would do that. Yeah, I mean, AI is doing it for you actually. So
perfect results.
And perfect results, yes. So what you could do is like, if you wanted, would be do something like, x equals x, sigma equals sigma, but yeah, let's maybe not do that.
Okay, that answers the question.
Yeah. Okay. No, I will do it properly.
So
X.
it's a constant.
Yeah, no.
Sigma equals.
Oh, actually,
What was sigma?
well, actually, it is necessary in this case because it's multiplying the log leg. It's not sum.
Oh no, okay, it's the 2 over 2 sigma squared that
And it is-
goes away, goes out from the sum.
Yes.
Wait.
Yeah, data is data. Yeah. Okay, so is it fine for this log likelihood function?
Mm-hmm.
Yeah. Okay. One thing, so now we want to explore the posterior, which is the probability of theta given the data. Which is the likelihood times the prior, normalized by the evidence. And here you can see that you have some objects that is coming from Erin, which already define a proper uniform distribution for your 2 parameters. So there are some basic distributions already implemented in Erin. But I think if you want to use your custom prior, you would need to use the same kind of object, right? And define it as a class. Is that correct?
You can define any distribution you want.
Yes. Yeah. So then we set up basically the MCMC sampler, this ensemble sampler, to explore the posterior distribution of theta given the data. And you choose the number of, these parallel workers I was telling you about, which are basically different MCMC chains that are running in parallel. And sometimes to do proposal, they exchange information. So here we set 20 of them. I don't know if there is a rule of thumbs for choosing this. Usually it's at least 4 times the number of dimensions. But the convergence rate should be better if this is quite high. Yeah. Would you agree? N samples is the number of iterations, basically, that you have. And then you need to define a starting point. So here we draw randomly from the prior. Okay. And then we can start sampling. Yes.
There's a sigma squared in log likelihood.
In the log likelihood.
1 by 2 sigma squared.
1 by 2 sigma squared. Thank you. Thank you. Thanks. Okay. Let's recollect the chains. So you know that there is this method get chain. So Erin can handle different models. You know, when you're doing, for example, Bayesian model comparison, and you want to test different models, possibly with different dimensionality. You can have different models. That's why there is a keyword argument. So sorry, there is a key here that says model 0. Then there is some reshape. So the 2 is because of the number of dimensions, right? Okay, so you can inspect the chains like this. So you know, as Stas was mentioning, you have usually a burn-in period where your MCMC chain is not stationary, and you can see it a little bit here, but it quickly stabilizes in that case. So you can, you know, say, okay, I throw away the first 1,000 points, 10,000 points, to produce the posterior distribution corner plot. And for this, we use this, you know, chain consumer I told you about. So you need to create an object, a chain consumer object. You need to add the chains. It has to be a Panda data frame. What you can do as well is adding the true location, so the injection, so that it draws, you know, lines at the right point. And so you get this. So something, obviously that is not perfectly centered on the true location because you have noise fluctuations. But the interesting thing is that you can compare this result to what would give you the frequentist approach. So in a sense, you can compute this covariance, for example, the theoretical covariance, and you can compute the empirical variance of the parameters that you obtain with these chains, and this will output you, well, something, right? Some numbers that you can compare. So that would be equivalent to comparing what you obtain with a Bayesian inference and what you obtain with the F statistics. The Fisher information matrix. So do you remember, what Stas introduced you about this? So basically, the Fisher information matrix would be this, the inverse of this covariance. And so if the posterior is sufficiently Gaussian, if you have sufficiently high SNR, these two, the variance of that and the Fisher information matrix give you similar results. It's not always true, but you have to meet certain conditions. Okay, it seems I had forgotten to put that blank, so it's fine. Sorry about that. So anyway, it seems that AI does that for us. So this least square covariance is what's implementing that. And what I'm also doing is taking the covariance of these samples, and I'm comparing the two. And you see that it is quite close. So in that sense, here, yeah, I would say that the frequentist approach and the Bayesian approach are agreeing quite well. Questions at this stage? No, that's fine. Okay. So, yeah, since this is done, we can switch to maybe more interesting things and do the same, but for a more complicated model that is a massive black hole binary waveform. So here we use a software that is called Lisa Beta that I told you about. It's written by Sylvain Marsa and John Baker. It has been optimized for frequency domain analysis. So there are, many approximations especially in the Lisa response that allows you to produce waveforms in milliseconds to 10 milliseconds. As Nikos mentioned here also, you could use another waveform generator that is called BBHX, developed by Michael Katz. This is under the thing. It's the same algorithm. It's Phenom-D or Phenom-HM models, phenomenological models, but this one is accelerated through GPUs. So what we will do right now is just create our own data set and play with it. So we don't introduce any noise. We just produce a time series with this generator, and then we play the game of analyzing this data and trying to recover some of the parameters. So obviously you see that there are many of them, right? That there are scale locations, there are angles of spins, there are spins magnitudes, the masses, the coalescence time, phase at coalescence, initial Poynting angle of the spins, I guess. No, this is not. The redshifts and distance of these actually, these are parameters that are a bit redundant. Okay, they are not all used in the generation, but you have a redshift and luminosity distance. Then you have auxiliary parameters that are useful to generate data, the waveform. This is observation, duration, and cadence. So basically, what the waveform generator will do is to optimize the frequency grid on which it will generate the waveform. It will generate as few points as possible, right? And then once you have this minimal coarse grid of points, you can interpolate between them. So it's a way of saving computational time. Okay, so here we arbitrarily choose a DD of 5 seconds. So the actual Lisa data will be sampled at 4 Hertz, so it will be 0.25 seconds. But usually to do the analysis, you can a bit downsample your data. Yes?
What is the cadence that is in the parameters above then?
This is indeed. They put 3 here. Okay. Yeah, this is you. Yes, This was an example of a parameter dictionary, but here you see then when we instantiate the fast BHB object, we set the sample cadence that we want. So maybe you're right. This was for a Sangria data set, but I don't remember it was 3. But anyway.
So Sangria was 5.
Yeah, it was 5 as well, right?
Okay, then for sure it's because we just looked with Martina yesterday and it was 3.
Aha. Okay. Okay, so spritz is another data set, so another beverage, but another data set as well, where instead of having a blend of sources, you have only one type of source, but which is corrupted by glitches and also interruptions in the data. So it's more targeted to, deal with data artifacts. Okay, here there is some renaming or reshuffling of parameters to fit the nomenclature of Lisa beta, because let's say the LDC usually nomenclature is a bit different than the one that is used by the waveform generators. Here you have a simple description, a very very quick description of what this waveform generator is doing. So basically what it does is it separately generates phase and amplitude of the waveform in the frequency domain. And owing to some approximation, you can write the Lisa response to this gravitational wave as a transfer function, TA, times the waveform in, let's say, the SSB frame or the source frame. So in principle, the Lisa response, even though the massive black hole binary signal is quite short, it depends on time. So usually you need to deal with the time variations of the response. But here it does it in a clever way, where you can still formulate everything in the frequency domain. Okay.
Where is the information of the orbit?
Where is the information of what? Sorry.
Orbits.
Orbits. I think so. It's okay. In the yeah. So it's a good question. So in this, I think waveform parameters as MBH here. This is a list of auxiliary parameters, and in this you could add the orbit that you want, right? You could tell what is the orbit that you want. Indeed, here it's a bit hidden under the rug. This is Keplerian orbits, assuming almost constant arms. Do you actually know what is what is
hidden somewhere?
Yeah. Okay. Yeah, I believe this is in this dictionary here.
I think it should make it clear that in principle we should also.
Yes. No, it's a good point. So basically what goes into this TA, which is the transfer function to go from, solar system barycenter frame, strain to the Lisa response. This depends on the orbit. This depends on the motion of Lisa around the sun.
And I think, if I'm not mistaken, I think someone wanted to do this, but I don't know if you finished this. Like if you have the actual physical orbits,
Right.
This frequency response could be changed a little bit.
Yeah.
So at the moment it's much simpler compared to if you have changing length of the orbit. So I don't know if he has implemented this or not.
Okay. Yes. So maybe some of the approximation that goes into this transfer function will have to be reworked. Yeah. Does BBHX take an orbit as input? Now, yes. Okay. So, the other waveform generator that I was telling you about, to it you can give an orbit file. Yeah, we are. Okay. Okay. So, what this does is generate the TDI signal. So on this TDI channel, here it's what we chose is the TDI channels A, E, and T, which are pseudo-orthogonal TDI variables. That means that they are approximately orthogonal under certain conditions on the noise and on geometry of Lisa. So it means that these the arm lengths should be equal, constant. Also, there are conditions on the noise symmetry. All the interferometric measurements in Lisa should have, well, at least by noise component, they should have the same power spectral density. So there is a lot of approximation that goes into the fact that A, E, and T can be considered as a orthogonal variable with respect to the noise, so uncorrelated. This will not be exactly true in practice. And so what this line does is to compute the waveform on a coarse grid of frequencies. And so here you have some investigations of the keys that goes into this object. And you see that there is this coarse grid of frequencies, there is the phase, and then there is basically the real and imaginary part of these amplitudes here. And here, we plot it for fun. So this is the phase, and this is the real part and imaginary part of TA. So these are the things that are sufficiently smoothly evolving so that we can interpolate them. So then we need to evaluate this waveform on a frequency grid that corresponds to our data, right? We had a time series with endpoints, and we will have an equivalent frequency grid. So in principle of endpoints, but we can restrict it a little bit, but it will be sampled differently than this native coarse grid. So this is what we do here. We choose the number of, we compute the number of positive frequencies, and we create a vector of Fourier frequencies here, which is called f-vec. And then we restrict it a little bit between f-min and f-max, which are the upper bound and lower bound of this coarse frequency grid. Yes? Yeah.
Why couldn't we directly generate the data on the final frequency grid?
So actually, yeah, I could have hidden that into an encapsulated waveform, but it was just to show you that actually the actual computation of the response is done on a coarser grid to save computational time, because this is costly, right? Evaluating this TA of f and psi, it involves the phenomenological waveform model. It involves the Lisa response, and so this takes more time than evaluating an interpolator or a spline.
Not just time, also memory. You won't have enough memory to do that.
Okay. Didn't know.
So you only set a minimum and a maximum frequency, but the number of points is automatically set during the waveform evaluation.
Yeah, actually, so when you create this object here, it chooses the number of points. So this frec here, it chooses something that is optimal. Let's say maybe it will be more coarsely sampled in spiral. And then when it gets to the, to the merger, then it will increase the resolution. Yes.
Thank you.
So I'm just trying to understand the plots that come right after this.
That what? Sorry.
Yeah, these plots.
These plots. Yeah.
Yeah. So the horizontal axis is actually frequency. So
Oh yeah, it's not written. I'm sorry. Yes, it is frequency.
So you have phase as a function of frequency. How does that work?
Yeah, phase as a function of frequency. So you know, it's just that you have your waveform h, and you can compute it in the frequency domain, and you can always write that as this, right? This is what we call phase as a function of frequency. Other questions? No. Okay. Then this is what I did to encapsulate a little bit the waveform. So this MBH object here is what we just created up, like above, this thing, you know, which is basically saying, okay, we are interested in the TDI variables, and we are interested in the 2-2 mode, okay? And then this is basically, you know, interpolating the phase and interpolating the real and imaginary part of the total amplitude that includes the Lisa response, and then you create the full waveform with that. This is something that we can reuse later. So, yeah, Nicholas had also put something else, which is showing that you could also, instead of doing this game of interpolating the phase and amplitude, you could also have used this evaluate TDI Frex series for channel 1, which is TDI A in that case. This, you can do that, but since it's evaluating all the TDI variables in a row, it might be not as efficient as just concentrating on one single channel, as we will do next. Because to save a little bit of computational time, we will just do the analysis on one single TDI channel. Okay, so now we will plot the waveform in the frequency domain in the TDI A variable, sorry. Well, using these two approaches, but they are equivalent. Okay, I also mentioned that here, we use this analytic noise object. It actually comes the LDC toolbox, which allows you to compute the power spectral density of the noise in the TDI channels. And you can specify the model that you use to compute this power spectral density. And psi RDV1 means the science requirement document of LISA that specifies requirements on the sensitivity. And you get this. So if you normalize properly as a density, I don't know how it's normalized here. Yes, I think it's density, one-sided density. You can visualize the waveform and compare it to the TDI A noise. Okay. You can do that for the other channels. So you have A, E, and T. So we do that as well. So here you can see that the T channel compared to the noise is attenuated. At least, you know, in this, under these assumptions, which means that for data analysis, you will not lose too much signal-to-noise ratio if you ignore the T channel. But first, we will only use the A channel to do the analysis. So now comes, you know, yes. Solano, could you send the...
Yeah, just a comment. I mean, I think what you say is right, that the T-channel does not contribute much here, but in the plot, you're comparing it to the PSD of A and E, I think.
Yes,
the T-channel has a different noise transfer function,
yeah.
So you should compare it to a different curve.
This is right, yeah. This is absolutely right. Maybe I could try to, let's try it to see if I can do it here. So let's see. So it's very dangerous to do that, obviously, but let's try it anyway. Okay. So here you can see, yeah, you can now compare, yeah, as you say rightly, the green curve to the actual power spectral density of this T channel. So dashed line is the T channel. And you see that actually, yes, it's less noisy in that particular noise model. So the SNR of the green is not so low as you know, as if we were comparing it to the other black solid curves. Does it make sense? Yeah. Okay. So now we can write down the likelihood, you know, in the gravitational wave way, let's say, where, you know, we define this inner product that you know now. We discretize it. We define the likelihood as you know, this inner product of the residuals. So data minus signal or signal minus data. And actually, the fact that we assume that these two channels A and E are uncorrelated means that we can add the two likelihoods together. So this next exercise is just you know, writing down the inner products and writing down the likelihood function based on this inner product for a single channel. So, are people already ahead, or are you doing that right now? I mean, just trying to assess. Yeah. I don't know if AI can write an inner product. Can it? It can? Yeah. No, it's not, huh? Yeah, but it's wrong. Am I right? Yeah, thanks. And for the likelihood, I always prefer the residual because I like that the likelihood is 0 when it's at the true waveform. Ah, it's bad, huh? Ah. No, he doesn't use the, well, okay. I want you to use. Ah. I hope I did not do any mistakes. Okay. Okay, here there is a test. So once you have written this likelihood, there is a test to see, okay, does it work? And you can also compute the signal-to-noise ratio of the signal by using the inner product. So it's, yeah, pretty high signal-to-noise ratio. So far, so good. Yeah? Okay. So let's go to the sampling. So as I said earlier, to make things a little simpler, we will do... Yes?
Sorry, can we just have like another minute?
Oh, sure. Yes, I'm sorry. Yeah, sorry. Let's wait. Maybe question, how would you write an inner product if the channels were correlated? So, because right now, you know, we always define this inner product with single channel, single PSD. Could be more complicated than that.
Probably I would say instead of the power spectral density, you should have something like variance.
Yeah, exactly. Yeah.
But I wouldn't know how to do it. I mean, I don't think that what I said is enough to
Yeah, but it's the idea, right? So instead of having this PSD, you have a spectral matrix for each frequencies, and so if you have so X and Y would be now, you know, vectors of you know, channel 1, channel 2, etc. Same for Y, and you would have something like this. So you would have Hermitian transpose of X times this inverse frequency matrix. Times Y. Okay, so it would be something like this. Yes?
The question is how safe it is to assume that the channels of Lisa are uncorrelated?
So it's not safe. Well, so it depends on which one you play with, right? If you use XYZ channels, so this Michelson variable that Olaf introduced to you, then these ones are completely correlated, even in the simplest assumptions. So if you do some assumptions of the noise, as I said, you can easily transform this XYZ set into AET. It's actually, linear function that doesn't depend on frequency, actually. And then you're safer. Let's say you at least, even if you have done some assumptions, you have a bit more. You have decreased the correlations between your set of TDI channels. But even so, these assumptions are not true in reality. So you will still have residual correlations in, AE, AT, ET will be correlated. So you will have off diagonals in the covariance that you ignore. So I mean, the problem would be that you would not bias your inference, but you would maybe underestimate your uncertainties, for example. That means that you would have posterior. You would get a posterior with some width, which it's actually not reflecting the real uncertainty that you have on your parameter. That would be the risk. Yeah.
And so what will we do?
So now, like many of the developers, they are switching to XYZ and say, okay, let's use that. And we know anyway that there will be some correlations, so there is less incentive to use some kind of pseudo-orthogonal channels, because anyway they will break. So let's model the full covariance matrix and forget about that. Another thing that you can do is saying, okay, I have XYZ, and under less assumptions with more realistic setup, and you can say, I can diagonalize this covariance matrix to find a set of TDI variables that are properly uncorrelated. But in a general case, this diagonalization will depend on frequency. Yeah. So this is fine if you're not, evaluating the noise parameters along the way. So if your noise model is completely fixed, as it is in this tutorial. But of course, in the global fit, you will also have to update the noise, right? So you'll have, once you update the noise, then you update this diagonalization, right, in the sense. So that's, yeah. Is it fine to go on? Yeah? Yeah, actually, I forgot that the one of the cells, takes time, but anyway. So, two things here that we do to simplify our life for this tutorial. The first one is reparametrization of some parameters. Instead of having the two masses, we will deal for the sampling with the mass ratio, and we will also use the chirp mass because this is, the parameters that we are most sensitive to. It lower correlations between parameters because, as you know, the chirp, the derivative of the frequency depends on chirp mass, and so we are very sensitive to this parameter in particular. And of course, also we restrict our inference to only 3 parameters, assuming that all others are fixed to their injected values. So yeah, some reparameterization. We take the data, which is now only the A channel in frequency domain. And so, okay, so here there is something to do, writing down the likelihood. This PMBHB fit is the parameter dictionary that you will use to generate the waveform by using this generate Lisa TDI signal underscore SMBH. And then you can use the likelihood function that you have written before. So there are three things, right? Creating this TDI object that contains the waveform on the coarse grid, interpolating the coarse grid on the required frequency grid, and then computing the covariance. So the input parameter vectors only contain chirp mass, mass ratio, and distance. We will break in 15 minutes, actually. Yeah, but you know, I will just stop. yes. So what I did is, first, creating this object that evaluates the waveform on the coarse grid, and I tell it take TDI and 2-2 mode.
So we're not standing over A.
Yeah, for now only on A. There is in the next section we will do that. Well, we won't have time, but there is a section where we can do that. It's just so that the sampling finishes on time. I need to check that. Where did I go? Yeah. Yeah, it was on. I don't know. It was on the solution notebook that he was telling me that. Maybe I don't know. So actually, yeah. Yeah, I should call that HTDI is better. I don't know. Can I use better names? So this MBHB TDI, has so a coarse grid, and also it's not an evenly sampled grid. That means that it's not the same DF as the resolution of your data. So you should always use the resolution of your data when you compute the likelihood. Yeah. If you were computing only signal-to-noise ratio, let's say, not doing inference, but computing a signal-to-noise ratio, you could use, you could consider that this, you just discretize this integral, and it's okay if you have a varying DF here. But here, we really, we are analyzing data, and so for each frequency bin that we have, we want to forecast the waveform, and this corresponds to really the resolution, the native resolution of your data. So. Yes, no, it's, ideally you would have DF. So maybe you could get DF indeed from F-vect, right? F-vect. You could say, okay, DF is, just the difference of two bins. Yeah, no, yeah, I agree. Yeah, actually, I need to check if the DF is correct. I think it is. Yeah. Where did we get it? Okay. Yeah, we got it from the observation time. Yeah. So, are there questions for this likelihood? No, it's fine. Okay. Do you need more time? Yes. Yeah. Yes. Oh, sure. Yeah, yes. Yes. As usual, in 5 minutes, we will do a coffee break, and we'll switch to Natalia's tutorial. So obviously there was too much here, but at least we went towards the massive black hole binary inference. What we can do is just maybe run the sampler while we are having the coffee break, and then we get the posteriors at the end. So if you want to test the likelihood, you can just pre-select the three parameters that we chose in the right order. And the likelihood should be very small. I mean, close to 0. Because in that case, there is no noise in the data. How's it going? Yeah. So before we go to the coffee break, we can set up the priors of chop mass ratio and distance. So chop mass is in solar masses. No dimension for the mass ratio, and I think this is megaparsecs for the luminosity distance. Maybe. Yeah, big range, yes. And so then we need to set the sampler. And the difference with before is that now we will take advantage of this parallel tempering method that Stas introduced to you. And we'll choose 5 different temperatures. So in principle, you should go a bit higher than that. But also this is for the sake of time. Number of walkers is 20. And number of iterations or like output samples is 2,000. You need also to specify the dimension of the parameter space, which is 3 in our case. So the way we activate this parallel tempering is just, providing this tempering keyword argument here to Erin. We also tell it that there is only one massive black hole binaries. So that's what this last instruction does. Because Erin uses this representation of branches for models, for different models, that would be like different sources, and then leaves for the number of sources inside branches. So, if you have multiple massive black hole binaries, you would need to have different leaves in this nomenclature, let's say. So here we will cheat, meaning that we will start very close to injection point to start the analysis. And this is what this cell does. And then we can start running the sampler. Yeah, exactly. So it should be, it depends also. So we can do break now? Okay.